The final speaker of this session is Dr. Yuki Takeuchi from NTT. The title of his talk is Efficiently Generating Ground States is Hard for Post-Selected Quantum Computation. Please start.
Thank you for the introduction, Chair. I'm Yuki Takeuchi from NTT Corporation in Japan. Today, I'm going to talk about our recent result on the hardness of efficiently generating ground states for post-selected quantum computation. This is a joint work with Yasuhiro. This is a joint work with Yasuhiro Takahashi and Seiichiro Tani from NTT. The detail of our result is given in this archive paper. Okay. As you know, generating ground states and measuring their energy are important tasks to explore several physical properties. Therefore, several methods have been proposed to approximately derive ground states, like these. These methods are nice and are practically important, but they can work for a restricted class of Hamiltonians. So we are interested in how hard to efficiently generate ground states in general. So our result is that we give evidence supporting that the efficient generation of ground state is hard by using the concepts in computer science. A little bit more formally, our result can be stated as follows. If there exists a family of post-selected quantum circuits efficiently generating ground states of any three local Hamiltonians, then the counting hierarchy collapses to its first level. The goal of this talk is to tell what this statement means. To this end, by using the remaining time, I would like to explain these three concepts: post-selected quantum circuits, three local Hamiltonians, and the counting hierarchy. To this end, first, I explain some complexity classes. I think some complexity classes have already explained by Tomoyuki, but just in case, please let me explain them again. A complexity class is a set of decision problems. Here, decision problems are mathematical problems that can be answered with yes or no. For example, is 1 + 1 equal to 2? This question is a decision problem, but what is 1 + 1 is not a decision problem. First, I introduced the most basic classical complexity class P. It is a set of decision problems efficiently solvable by a classical computer with no error probability. So if an instance whose correct answer is yes is given to a classical computer, it outputs yes with probability 1. On the other hand, if the instance whose correct answer is no is given to the classical computer, it always outputs no. In other words, it outputs yes with probability 0. So by allowing small error probability, we can generalize this class to BPP. In this class, if the instance whose correct answer is yes is given to the classical computer, it outputs yes with some high probability, such as 2/3. In other words, on the other hand, if the instance whose correct answer is no is given to the classical computer, it sometimes accidentally outputs yes with some small probability, such as 1/3. In this class, the difference between these two probabilities is constant. In this sense, we say the error probability is bounded. The B of BPP is an abbreviation of bounded. So by making this error probability unbounded, we can also generalize this class BPP to PP. In this class, the difference between these two probabilities may be exponentially small. In this sense, error probability is unbounded. Furthermore, by generalizing this class, we can introduce the counting hierarchy. It is an infinite tower of complexity classes that generalize PP. The zeroth level of the counting hierarchy is P. The first level is PP. The second level is PP to PP. In order to explain what this class is, please look this figure. In this figure, the PP machine is a virtual computer that can efficiently solve any problem in PP. In other words, problems in PP can efficiently solved with a single PP machine. On the other hand, in this class PP to PP, one more additional PP machine can be used to solve the problem. So for example, if the input is given to the first PP machine, this machine can interact with another PP machine to solve this input problem. Then finally, this PP machine outputs yes or no as the answer. So as you can expect, the third level is PP to PP to PP. In this class, two additional PP machines can be used to solve the problem. By doing so recursively, we can define the infinite number of complexity classes. The counting hierarchy is the sum of these infinite number of complexity classes. And many computer science researchers believe that the counting hierarchy does not collapse. For example, if the counting hierarchy collapses to its zeroth level, it means that the counting hierarchy becomes equivalent to P. In this case, we can show that P is equal to NP. Here, NP is a set of decision problems that can be efficiently verified with a classical computer. This equivalence is considered to be strongly unlikely in the field of computer science. So we can say that the zeroth level collapse of counting hierarchy is extremely unlikely. In the similar way, we can say that the first level collapse of counting hierarchy is also unlikely. This is because if this collapse occurs, we can show that PP includes the polynomial hierarchy. That is a NP analog of the counting hierarchy. So by replacing PP with NP, we can define the polynomial hierarchy. This inclusion is also considered as an unlikely relation by, in some papers such as this one. And as I said, our result use this first level collapse of the counting hierarchy as an unlikely consequence. Okay, and at the last of classical complexity classes, I introduced Pspace. It is a set of decision problems solvable by a classical computer with no error probability by using only a polynomial amount of space. As a difference between P space and P, in this class, we are interested in the amount of space rather than the required time. And this figure shows the known relations between classical complexity classes where I have explained. Okay, next, I introduce some quantum complexity classes. The first one is BQP. It is a quantum computing analog of BPP. It is a set of decision problems efficiently solvable by a quantum computer with a bounded error probability. So the difference between BPP and BQP is to use quantum computer or classical computer. Other parts are the completely same as BPP. In order to derive our result, we have to consider the post-selected version of BQP that is called post-BQP. In this class, one additional measurement is added to the quantum circuit. And this additional measurement is called the post-selection measurement. And the requirement for this post-selection measurement is that the probability of P being 1 is at least the inverse of an exponential. This requirement is satisfied for almost all of quantum circuits. So yeah, and in this class, we are interested in the conditional probability like this. So this is the difference between post-BQP and BQP. In BQP, we are interested in the probability of O being 1. On the other hand, in post-BQP, we are interested in this conditional probability. In other words, post-BQP is a class of decision problems that can be efficiently solved with a universal quantum computer if we can select the outcome of post-selection measurement as 1, as our wish, as our desire. Of course, in the principle of quantum mechanics, we cannot select the value of outcome of the measurement as we desire. But in this class, we assume such a virtual capability beyond the quantum mechanics. By assuming such a virtual power, we can define the a useful complexity class like post-BQP. Indeed, for example, in 2005, Aronson have shown that post-BQP is equal to PP. Roughly speaking, this means that quantum computing model inspired from the quantum mechanics is equivalent to a computing model inspired by classical mechanics. So this equivalence implies some close connection between quantum mechanics and classical mechanics. And furthermore, this class post-BQP is useful in to derive our result. Okay, this is a summary of complexity classes where I have introduced. Among them, Pspace is Pspace is closely related to the Hamiltonian. This is because the precise three local Hamiltonian problem is a Pspace complete problem. Roughly speaking, Pspace complete problem is the hardest problem in Pspace. This problem is similar to a local Hamiltonian problem explained by Tomoyuki, but this problem has some difference from the local Hamiltonian problem. Before I explain the difference, I explain what the three local Hamiltonian is again. It is an n-qubit Hamiltonian represented as the sum of a polynomial number of 3-qubit Hermitian operators like this. Here, as an important point, the local does not mean the geometrical locality. So, of course, this Hamiltonian may include the term that denotes the interaction between three qubits that are geometrically local. But at the same time, this Hamiltonian may include the term that denotes the interaction between three qubits that are not geometrically local. So the family of three local Hamiltonian may include some artificial Hamiltonians that are not not natural in a physical sense. By using the three local Hamiltonian, we can define the precise three local Hamiltonian problem as follows. Given a three local Hamiltonian and two real numbers A and B, satisfying this inequality, decide which case holds. The ground state energy is at most A or at least B. So in order to solve this problem, we have to distinguish between these two regions, no regions and yes regions. The distance between these two regions are exponentially small. That's why we say this problem is precise. And the local Hamiltonian problem explained by Tomoyuki has a polynomially small gap between B and A. So this is a difference between his problem and this precise three local Hamiltonian problem. Okay, now we can understand what this statement means. This statement implies that the efficient generation of ground states of any three local Hamiltonians seems to be impossible, even if we can use the post-selection ability that is beyond the quantum mechanics. This is because it is believed that the counting hierarchy does not collapse. And some hardness results for the efficient generation of ground states have already shown, but they are shown for universal quantum computation without the post-selection. So in this sense, our result improves the previous hardness results. Okay, finally, I briefly explain the sketch of the proof. What I have shown is that if there exists a quantum the precise three local Hamiltonian problem is in post-BQP. By showing this statement, we can say that Pspace becomes equivalent to PP. This is because the precise three-local Hamiltonian problem is Pspace complete, and post-BQP is equal to PP. If when Pspace and PP becomes equivalent, the counting hierarchy also becomes equivalent to PP. This is because the counting hierarchy is between Pspace and PP. Okay, this is a list of my outlook. That's the end. Thank you.
Thank you very much. Thank you very much. The session is now open for questions and comments, discussions. So Yoshioka-san, please.
Hi, thank you for a very nice talk. What happens if you lift the condition that it have to be precisely determined? What if you allow for example, polynomial gap or constant gap between the decision?
Oh, you say about this gap?
Right, yeah.
In this case, unfortunately, our proof does not work.
Mm-hmm.
But on the other hand, if even if this gap becomes the inverse of a polynomial, it is open whether we can generate the ground states of such the Hamiltonian by using the post-selected quantum circuit. And so, yeah, I'm also interested in such a question. So now I'm working on that topic.
Okay, thank you.
Yeah, thank you.
Hayakawa-san, please.
Thank you for the nice talk. So I have two questions. One question is that so if we can prepare some kind of trial state which have an overlap with the target ground state, so then post-selected then quantum computer with post-selection can I think then quantum computer with post-selection can efficiently generate ground state. So does your result means that preparation of such trial state which may have overlap with the ground state, so that the overlap can be exponentially small is difficult?
Yes, I think so.
Okay.
Yeah.
So then my second question is that so you actually used was that the Pspace collapses to PP. So
yes.
So I think it is more preferable if a certain, so for example, fifth level of series collapses to each PP. Such kind of thing is more unlikely. So do you think you can improve the statement to some lower level of CH?
Yes, one of my outlook is that question.
Yeah.
So I think this question is very, very interesting, but I don't know how to do that. One possible approach is in order to show our result, we consider the post QMA that is equivalent to Pspace, but we can also consider the post QMA2 that is equivalent to exp or next by considering more more wider class of complexity classes, yeah, it may be possible to show more unlikely result. But I don't know how to relate the decision problems motivated by Hamiltonian with such a higher class like post QMA2. I think if it is possible, then I can obtain some more unlikely result. Yeah.
So you need more difficult local Hamiltonian problem.
Yes, that's right. That's right.
So thank you.
Any other questions? Nakata-san, please.
Thank you for a nice talk. I have a quick question. What is the local dimension of this precise three-local Hamiltonian?
Oh, so in this case, we don't consider the dimension, so there is a possibility where the dimension is n in the worst case. So
N.
yeah, this is because we don't restrict the interaction between 3 qubits. So
it can be anything, basically.
Yeah. So
I actually wonder, so there's a Hamiltonian, like it's there's a Hamiltonian whose what is that? Hamiltonian problem is undecidable, right?
Oh, deciding the spectral gap or something.
Yeah, spectral gap.
Yes.
And okay, this is very naive kind of intuition, but I think that Hamiltonian, the local dimension is the like 100 or something. Well, it's finite at least. So if you use that Hamiltonian in this in your construction, is your statement directly follows from that the undecidable Hamiltonian?
I think
too naive.
The class of Hamiltonians is different between our result and their undecidability result.
And the point is three local or?
I forget the detail, but
yeah, sorry, I also forgot the details of the undecidable Hamiltonian, but I just want to know
if I correctly remember, in their problem, some promise is required for the spectral gap.
Right.
But such the restriction is not, such the promise is not required in our case. So
I see.
I don't know. Yeah, these two classes are the same or not. Yeah.
I see. Yeah, there should be a promise in the undecidable Hamiltonian.
Yeah.
So that's different.
Yeah, but I think it is interesting to derive the undecidability of measuring energy or something from their result. Yeah.
I see. And also it's interesting if you can reduce the local dimension.
Yeah. So
as you know, the main criticism of this from the viewpoint of physics is we often use like 10 dimension or 100 dimension or one particle. So, but in physics, we often interested in the like 2 dimension or 3 dimension or something like that.
Yes. And indeed, for non-precise ordinary local Hamiltonian problems, 1 dimension is enough. We replace the qubit with qdit with a constant d. So if such a technique can be used even under the post-selection, we can show the hardness for such a local dimension. Yeah, but I don't know whether such a technique correctly works even under the post-selection.
I think, yeah, it's very nice if you can prove it.
I will try it. Yeah, thank you.
Okay, thank you very much.
Thank you.
Any other questions?
Can I ask a question?
Yes, please.
So in your slide, you say precise 3 local Hamiltonian is P space.
Yes,
And is it not known whether precise 2 local Hamiltonian problem is P space?
yes, that's right. I think so.
This is because the perturbation technique that it is not known how whether perturbation technique works for this precise case.
Yeah, I think so. Yeah.
Okay. And why you can show 3 locality? So if you usually you need 2 qubits for clock register and 3 qubits for clock register and 2 qubits for gate operation. So this means 5 local Hamiltonian. Why in that case you get 3 local Hamiltonian?
If I correctly remember, the reason is the same as for non-precise 3 local Hamiltonian problem. Yeah. If I correctly remember, the reduction is essentially the same.
Okay. And in your proof, so what you show is it's impossible to generate ground state of Hamiltonian with exponentially precise fidelity.
Yes, that's right.
And this exponentially precise fidelity is essential to show your reduction to P space.
Yes, that's right.
So what happens if this fidelity is only polynomial, 1 over poly?
Oh, this is because in the class related to the post-selection, we have to consider the conditional probability. So the probability of P being 1 is one emerges as a denominator. So in order to deal such the denominator, we have to assume the exponential accuracy. Yeah.
So for 1 over polynomial fidelity, can you show some impossibility result?
At least our proof does not work for that. So for such a case, but in principle, I don't know whether we can show it. Yeah.
Okay. Thank you.
Yeah. Thank you.
Any other questions? Okay, if not, because time's up, let's thank Takeuchi-san again. Thank you very much.
Thank you very much.
And I like to thank all speakers in this session. And is there any announcements from organizers?
I don't think so. Thank you very much for sharing this session.
Okay. So
again, please make sure
yes.
to send the slides.
And please check the announcement in the chat from Ugajin-san. So the next session will start at 10 o'clock in Japan time. So see you later.
Yeah, enjoy also remote time. And so
yeah.
Thank you very much for wonderful talk of speakers, and thank you for participation. So let me close this session in just now.
Thank you very much.